running at a time. But that's how a database could support lots of different clients, making each of them that individual promise, and still allow developers to create systems that make sense. And then kind of fast forward to the age of the web, the age of mobile, and now the age of containers and in Kubernetes, and you've got all sorts of different nodes all over the place. Some of them contain their own data, and you have to make sure that you uphold these 4 promises. So that brings you into this world of distributed transactions. So you think about what has to happen with a distributed transaction. You've got 2 different data stores, right? And your application might be hitting either one of them. It might be doing a read against one, and then it has to do writes against another, because that's just a read replica. It needs to serialize its writes to the master. And
okay, I found this on the web for license.
And so don't say serialize around your iPhone. And so in order to uphold these 4 promises across distributed databases, you basically have to have the databases coordinate in order to give you these 4 promises. And you have to have that coordination happening inside of the different contexts, the different fundamental units that are the distributed transactions. And so, as you might expect, this puts a lot of burden on the database itself in order to give you these promises. Now, fortunately, some really smart people worked on making distributed transactions work. One of them, a guy by the name of Pat Helland, he actually was working at Microsoft in 2009. He was one of the people that helped to build the distributed transaction coordinator for Microsoft. And so he figured out all of the ways in which these databases had to communicate with one another in order to make sure that that the ACID promises were upheld in a distributed transaction. And so he collected all of these truths, these algorithms, in a paper called "Building on Quicksand," where he's talking about the fact that we can build something as robust and as rigid as an ACID transaction on top of the quicksand that is the ephemeral network that we're communicating over. So he says, yeah, I know the fallacies of distributed computing. They're real. And yet, on top of that quicksand, we can build something like a distributed transaction. And this is how we do it. You have to have all of these things talking to each other and waiting for confirmation, and then acknowledging things, and then writing a transaction log, and then taking a snapshot at a checkpoint and moving things forward. And so you make all these things work, and then, hey, wow, look, you've got distributed transactions. That's a lot of work. I mean, not just for the team that built the distributed transaction coordinator, that's a lot of work for SQL Server. That's a lot of work for your node. That's a lot of work for the machine, for the database. And now your application is waiting on all that work to be done. So if you've ever built an application against the distributed transaction coordinator, you might have not been very happy with the scalability of that application. Maybe even the reliability under certain configurations was not what you wanted it to be. And that's because the database is just doing an awful lot of work for you. So in that same paper, Pat Helland told us what we can do to our applications in order to not require the ACID properties from the database. So it's like, okay, you can take these promises, but they're expensive. Or you can take on a different set of properties that you yourself implement, and now you don't need those promises. And he called that set of properties ACID 2.0. So ACID 2.0 is this set of 4 properties. Hey, they all start with ACID. Associative. You might recognize this from mathematics. The associative property means that you can put the parentheses around any group of an operation, and you'll get the same answer. So addition is associative. You can put the parentheses around any pair in a long addition, and it'll give you the same sum. Commutative, another thing from algebra. You can do things in different orders, and you'll get the same results. Just like addition, 5 plus 3 is equal to 3 plus 5. Idempotent. That one is a mathematical property, but one that that we sometimes don't hear a lot about. Of course, if you're familiar with HTTP, you know about some idempotent verbs. It basically means that if you do the same thing twice, you'll get the same answer as if you did it just once. So those are all mathematical properties, associative, commutative, idempotent, that you can find in literature, in mathematics. Distributed. That one seems a little bit strange. It's like, well, of course, I'm writing a distributed system. I want something to be distributed. What does it mean for my application to be distributed? Not just that it runs in lots of different places. By distributed, what he's talking about is if you perform the same operation at any one of those nodes, you'll get the same result. So these are all about getting the same result under different conditions, based on grouping, based on order, based on repetition, and based on location. So the ACID properties are properties of your application, where it takes on the guarantee that if you do something within that application, then it's going to be associative, commutative, idempotent, and distributed. And if you take on those 4 properties, then you don't need the ACID properties of the database anymore. You don't need distributed transactions, and hence you scale better, you're more robust, things work out better. Okay, well, let's dive in and let's see if we can understand why this is true and what this all means. So there are 2 hard problems in distributed systems. 2 exactly once delivery, 1 guaranteed order of messaging, and 2 exactly once delivery. And just like all jokes, this one is absolutely true. There is, it is really difficult in a distributed system to guarantee that your message is going to arrive just once. You might get a network partition and you have to retry. If you have to retry, then that means that that there's the possibility that you send the message twice. Maybe the network partition happened on the response. So you have to, the server has to recognize, hey, I already saw this message, and I have to make sure that I get the same result as if I'd seen it just once. Guaranteed order of messaging. If you have a queue anywhere in your system and you allow, you collect messages that have failed into a dead letter queue, you're going to move them out of order. Other things are going to flow through. Now, hours later, perhaps, an administrator is going to look at that dead letter queue and say, oh, okay, fix, send. Even if it's not a dead letter queue, you still have different systems publishing to different topics and subscribing to those topics, and things are going to get out of order. Things are going to pass each other on the myriad of paths that occur in a distributed system. So it's really hard to guarantee exactly once delivery and order of messages in a distributed system, which means that we have to write our systems to tolerate those 2 things. You know what? That sounds like 2 of the ACID 2.0 properties. So let's take a look at those. We've got the idempotent property. And so we recognize idempotence from HTTP. Let's suppose that I've got an HTTP resource at people/42 that gives me the value name Bob. And now I'm going to put to that same URL name Robert. So that's going to update that record, and now name Robert is the value. Well, what if I were to put to people42 name Robert a second time? Yeah, maybe I didn't get the result. Maybe things just timed out and I tried again. Whatever the reason, if I do that a second time, I'm still going to end up with name Robert. So that means I've done a thing twice, but the result is the same as if I had done it once. So this is the idempotent property. It's kind of built into the very nature of HTTP puts and patches and deletes, that once you've put, patched, or delete a thing, doing it again doesn't change the state because you're just telling it what state to be in. Not true for post. Post, you're saying, hey, create a thing. If you say, hey, create a thing a second time, you're going to get a second thing. So some HTTP verbs guarantee idempotency, some do not. That's simply the semantics of the verb. But that takes care of the once and only once delivery guarantee. That if you can't guarantee that, I can just make sure that my handler is idempotent, and then we're good. Okay, so then what about the other one, the guaranteed order of messages? Well, that maps nicely onto the commutative property. So let's suppose that we built this online game where we're doing some kind of a word search. So you've got like a boggle board, all the different letters, and you're looking for words in there, and you're scoring your words. So you say, all right, found the, all right, score 3. Now you have a total of 3 points. All right, oh, I found there, score 5, total of 8 points. So if we sent those requests to the server and they happen to get out of order, then we would have scored 5 points and then scored 3 points. Still, we're up at 8 points. We got the same results, even though the messages arrived out of order. That's just simply taking advantage of the fact that addition is commutative. So the message handling ended up being commutative. So that means that our system can handle out of order messages just fine, because all it's doing is adding. Okay, so that's great. We've got some things that are idempotent, some things that are commutative. So that means we can take care of the 2 hard problems in distributed computing, right? Well, not quite, because that thing that was idempotent, it might not be commutative. So let's take a look at the HTTP put again. So I've got my resource with name Bob, and I'm going to put to people42 name Robert. Now the current state is name Robert. What now if I put people42 name Larry? What's the current state? You guessed it, it's Larry. The question is, what if I got those out of order? Then I would end up in a different state than I had the first time through. So that means I've received the messages in a different order, and because of that, I came up with a different result. Sometimes known as a race condition. If you depend upon the order of messages, you are not commutative. So you can be idempotent, but not commutative. So not a great design. The opposite can also be true. So in this case, we saw that we were commutative, but we are not idempotent. So we scored 3 points, we scored 5 points, we're at a total of 8. Well, what if we score 5 points again? So you see that that second score come in, or that 5 points come in a second time. Now we're at a total of 13, which may be great for us, but not for our opponents. And people certainly wouldn't want to keep playing that game. So this system is commutative, sure, but it's not idempotent. So we really need both in order to solve the 2 hard problems in distributed computing. So it's not that we pick and choose which of the ACID 2.0 properties we take on. We have to have them all. So that gets through two of them, idempotent and commutative. Let's talk about some of the other properties. So the next one is the associative property. And in a distributed computing architecture, this might show up as an aggregation of, like maybe doing a reporting server. So you're taking, all of the day's transactions and you're processing them in your online transaction processing, one at a time fashion. But then when you get to the database, you don't want to have a list of the individual day's transactions. You want the database to be a nice little star schema that you can just query it and say, okay, what was the total for that day, and it just gives you back the answer. So so you should be able to take all of these, batch them together, send them to the database, and then it ETLs them in, and now you've got your reporting database all set up. Now your boss comes to you and says, okay, I need those reports. Instead of running them daily, I need them by the hour. Can you do that? You say, sure, let's just tweak the schedule. So now, as opposed to batching them by a day, you're batching them up by a smaller amount. You're batching them by hour. You've basically put the parentheses in a different place. So you said, okay, I've now, instead of grouping a whole bunch of things together, you're grouping a smaller set together, and then you are applying those operations one after another. You really should come up with the same answer as if you had done it by the day. Your boss would be very suspicious if the numbers turned out to be different at the end of the day than his daily report showed. So whether you batch them up one way or another way, when you move those parentheses, you should get the same result, and that's the associative property. So, and by the way, any questions, any clarification, please just unmute and ask away. I don't mind the interruptions at all. At this point, we have talked about 3 of the properties, and these are the 3 that you can look up in a math textbook and you can see what those definitions are. These are properties of mathematical operations. And when you have a system that has a set of properties, mathematicians like to give those things names. And this set of 3 properties has a really cool name. It's called a semilattice, which, when you first look at it, is like, why would you give a name like semilattice to those 3 things? That doesn't make any sense. It's just mathematicians making stuff up. Well, you're software developers. You make stuff up all the time too, so cut us a break. Mathematics and software, the 2, besides medicine, the 2 most jargon-rich fields that you could possibly think of. So semilattice, that's a walk in the park for a mathematician. You should see some of the other terms. But I'll try to give you a kind of an intuitive sense for what the word semilattice means. So imagine that you're starting at this value x, and now you can apply some operation. We're just calling it hat. It stands for some arbitrary operation that we haven't yet defined. So you're applying an operation to x, and that moves you forward to some other value. So let's say the values you can move to, based on what other values you mix in with x, are all in this space, this cone that's pointing out from x, and it extends infinitely. I kind of like to think of this as analogous to in physics. We know that causality, things can't affect other things at faster than the speed of light. So there's a concept in physics that when an event happens, right here at that time in space, there's a sphere that expands at the speed of light from that event, that point in space and time. And the only things that event could affect are inside of that ever-growing sphere. Well, if you take that sphere and you map it out in space-time coordinates. Now you can see as time goes this way, the sphere expands, you get a cone. That's the light cone. So all future events, all future causes, all future effects of a particular cause are in that cone. This is a mathematical way of expressing that, where you've got this value x, something's going to happen to it. Whatever happens to it, you're going to end up inside of this cone. So that's what we mean. Let's take a simple example here. Let's suppose that we were talking about the property of addition, and we were just talking about the positive integers. So that means that this cone represents all of the values that are greater than x. So you take any positive energy, add it to x, you're going to get a greater number. So that's what the cone represents. So the idempotency property means that if you take x and you combine it with itself, you apply the hat operation to x, you're going to stay right there at the vertex of that cone. You're not going to move. So that's kind of visualized by just this being a well of, you're going to try to escape x, but as long as you're just doing x, you're going to stay put right where you are. And so you can kind of think, okay, that's related to the idempotency that we talked about before, because I just did x in order to get here from 0, presumably, which was back there. So I just did x, and now I'm going to do x again. I'm going to stay right where I am. So doing a thing twice keeps you right where you are. So that's idempotency when viewed kind of mathematically. So now let's mix in the commutative property. So commutivity means that I've got these two starting points, x and y. And so they each have their own future cone. We can move from x into the green cone. We can move from y into the blue cone. So now we combine x and y together. We're going to end up at their intersection, x hat y. Now it doesn't matter if I started from x and moved up into the y cone, or if I started from y and moved up into the x cone. I'll still end up at the same place. That's the commutative property. X hat y is equal to y hat x. So now you've got this brand new cone, this blue-green cone, that's the starting point at x hat y, and everything in its future is in that little blue-green cone. So pretty cool visualization. I love it. But now let's bring in associativity. So with associative property, we can put those parentheses anywhere we want. So that means that we can combine three things, x, y, and z, by putting the parentheses around x and y or around y and z. And we'll end up with the same answer. Well, you can visualize that by saying x hat y is the tip of that blue-green cone. And now I combine z. So blue and green and the red intersect right there at the orange cone x, y, z. Or I could have started at y hat z and mixed in x. So it doesn't matter if I start with one grouping, x hat y, or another grouping, y hat z, and then mix in the third variable, I will always end up at the same result. So that's the associative property. So now taking a look at this diagram, we can start to see why mathematicians call this a semilattice. I mean, if you go out into your backyard and you take a look at a trellis, your roses growing up the trellis, you'll see that it's in a lattice shape. So it's made up of all these little diamonds. So the diamonds are shapes that are closed at the top and the bottom. So they kind of collect things up at the top, collect things down at the bottom. Well, a semilattice is closed on one side but open on the other. So this shape of intersecting cones is a semilattice. So I really love this this visualization because if you can think of an operation that has these three properties, then that means that that it has this ability to move something into the future by combining it, and you know that that it's going to reach that that gravity well there, that the lowest point in the cone when it combines those values, no matter how you get there, no matter how you do it, no matter how many times you repeat it. And that solves very handily the distributed systems problems of once and only once delivery messages, out of order messages, and grouping things in batches. So idempotency, commutativity, associativity, taken together is a semilattice. So that's a lot of math. Yeah, again, if there's any questions about that, please, by all means. I think one of the things that will help to really cement what a semilattice is to take a look at an example. Since mathematicians have studied these operations and given them a name, they've certainly given us examples of those operations. And my favorite example is a set union. So I've just replaced the hat with the union symbol. So now we can take a look at what set union means, and we can see that it is idempotent, commutative, and associative. So let's take a look at idempotent. If I've got a set car and a set car, union them together, I'm going to get the set car. So taking any set, union it with itself, you're going to get the same set. Why don't you get the set of two cars? Well, that's because sets don't count things. They just contain things. So you can't have a set with some number of individual elements in it. It's either in the set or it's not. So if the set contains car, union it, the set still contains car. So that means that set union is idempotent. Commutative means that I could take a set car and a set bicycle, union them together, and I get the set car bicycle. Or conversely, I can take the set bicycle, set car, union those together, I still get the set car bicycle. Why don't I get the set bicycle car? Well, because sets don't order things. They don't know which one came first. They just contain things. So it's the same set, no matter how you say it. So you can arrive at that set from either of those two directions, and you'll get to the same place. Now, let's take a look at the third one, associativity. So I start with a set car and then a set bicycle train. Union those together, and what do I get? The set car bicycle train. Very simple. But now let's suppose that I started with the set car bicycle, and then I union the set train. As you might expect, I still end up with the same set, car bicycle train. And that's because it doesn't matter how I've grouped things together. When I do the set union, it just contains everything that was in either of those two sets. So that means set union is associative as well. So that means that you could actually use set union as the only operation that your distributed system does, and the only data set that it stores is a set. And so if that were the case, your distributed system would just naturally be idempotent, commutative, and associative. It would handle out-of-order messages just fine. It would handle duplicate messages just fine. You could batch things in any order, in any grouping, you would still end up with the same result. So, hey, maybe we should build all of our applications based on sets. Maybe that's the fundamental data type rather than the object. I don't know. But so far, we've only talked about these three: idempotent, commutative, associative. And there was a fourth one. And that fourth one was distributed. So remember, the distributed property just means that no matter where I do a thing, I'll end up with the same result. It seems like this one is kind of a gimme. All of our systems are deterministic, right? So you do a thing here and you do a thing there, and it's going to give you the same result, right? There are some operations that we do that are not quite distributed. In fact, some database operations, some inserts that are not quite distributed. If you have a database that has an auto-incrementing ID, you're not going to get the same ID if you insert into one database versus inserting into another database. It's going to have different number of rows. They will reach different places within their lifespan. So why is that a problem? Well, let's suppose that you've got a live backup. So you want to at any point be able to swap over to this backup if that one goes down. Well, that means that you're doing a bunch of inserts over here, and it's doing some log shipping, get them all over here. So you're taking all these IDs and popping them over there, and then failure. All right, switch over here, insert. Something's still in the log. It hasn't quite gotten there yet. So you do your insert, and you're going to get the same number as that database that just failed has put into the log. So you will end up duplicating that ID if you try to swap over too quickly. Or conversely, you'll have to wait, that insert's going to have to pause and wait for the transaction log to drain, and then start up from there. So so you're starting to put those constraints back on the database again. Better if you can just guarantee that no matter which system you hit, you're always going to get the same result. And there are ways that we could accomplish that. And we're gonna talk about one of those ways. Actually, we're going to talk about two of those ways. But to kind of summarize the ACID 2.0 properties, they aren't promises that the database makes to you, like ACID 1.0. These are promises that your application makes in order to not rely upon promises from the database. And so they're associative, commutative, idempotent, distributed. I can group things, and I'll get the same result. I can swap the order, get the same result. Duplicate, same result. Different location, same result. So that is ACID 2.0. So let me pause if anyone has a question before we get into some examples. All right. So let's start with a nice little example. We've done file new project, and we've created a mobile application. So so maybe we just fired up ASP.NET and created an entity framework database, and then we wrote a Xamarin Forms application, and so now we've got this whole thing working soup to nuts. This is the kind of application that you will get out of file new project. Is let's suppose you've got this contact application. You're entering people into your app, and so the app needs to send that person to the backend in order to persist it. So it's going to post, so /people. That's going to hit the web tier. Web tier is going to turn that post into an insert, send that off to the database through entity framework, whatever. Database is going to insert that record and then generate an ID for that person. So we're using auto-incrementing IDs here. Now, in order for the web application to know the identity of that person it just created, it needs to use add identity or something like that in order to say, okay, what number did you just generate? Okay, thank you. And so there's the number 42. Okay. Now I'm going to pop that number 42 onto the end of a URL, send that back to the mobile app. And so from now on, that person's identity is people/42. If you want to update them, you put to that URL. If you want to delete them, you delete that URL. That's their identity. So in the meantime, what's your mobile application doing? Well, the user of that mobile app is probably going to want to now take a look at that person's screen and see the results that they just entered. They might want to be able to perform some actions on that person. So share this person with somebody else, or update this person, or that was a mistake. Let me just go ahead and delete them. Pretty much their next action is going to require the identity of that person record, but they don't have the identity yet. They're waiting on the web tier to return that 201 created. So, okay, we're going to wait for the web tier. The web tier, meanwhile, it's going to do that insert, And meanwhile, while it's waiting on the database, it can't talk back to the mobile app. It can't say, okay, I got your request. Here's the identity of the person. It has to wait on the database to generate that ID. So the only time that we can get back to the user and unlock their experience is when we've completed that whole round trip all the way from the mobile device to the database and back again. And only at that time do we have the identity of the object that the user just tried to create. So they're waiting through that whole process. So what ACID 2.0 properties have we violated here? Well, let's take a look at associative. Well, we're just doing one person, so we're not really doing a group of things. We're not batching, so we don't really have to worry about the associative property in this case. How about the commutative property? Well, if I post to one person and then post to another, or post to people once, post to people twice, and I happen to just do it in a different order, sure, those numbers, 42 and 43, would come back for the different objects, but I would still end up with two people. So conceptually, I still have the same result. So maybe you could argue about commutivity, but that's not the big problem. The big problem is with the other two. First of all, idempotency. And this type of application is not idempotent. And why is that? Well, that's because post is not idempotent. So I post to /people, name Robert, and now I get back an identity, 201 created, the URL is /people42. Oh, something, hit the wrong direction. Something happened and I have to do that again. All right, post to people, name Robert. Maybe it timed out. Maybe I entered a tunnel and didn't get the result, and so I have to wait until I leave the tunnel and hit the button again. Now I get back people 43. Post is not guaranteed to give you back the same object if you post the same request twice. So it's not going to behave in an idempotent manner. It's not just that we ended up with two different IDs here from the same database, it's that we ended up with two objects in the database. So the result is fundamentally different than if we had just done it once. So this is a problem. We probably need to fix this, but it's not the only problem. The other problem is that this is not distributed either. And that's because if my first post goes to one database, maybe it will come back with people 17. And then I have to repeat that post for whatever reason, goes through the load balancer, gets shuffled off in a different direction, and I end up with people 351. I've got two different identities for conceptually the same thing. And when those two databases talk to each other, they will not be able to talk about the same object with those same identities. Presumably the one that gave me the number 351 already has a 17 somewhere in there, and it means somebody completely different. That means that I can't take this identity and use it on any different node and get the same result. So if I later put to people 17, I'm going to be changing a different record based on which database I hit. I delete people 17, I'm going to be deleting a different record based on which database I hit. So this system is not distributed either. Fortunately, there is one solution to both of these problems, and that's calling back to something that that we looked at earlier. Let's use put. So if post isn't guaranteed to be idempotent, but put is, let's go ahead and use that. So now I'm going to come up with the identity on the client. I'm going to say, okay, I'll make up an ID. We'll call it Bob1945. So I'm going to put to that desired ID Bob1945, name Robert. And so the identity that I get back is going to be people Bob1945. Well, I already knew that. I knew that was going to be the identity because that's what I chose for it from the client's perspective. So now as a client, if I need to retry that, I'm going to put to People Bob 1945. The identity is still People Bob 1945. So I haven't changed the identity just because I've repeated the operation. So I've solved the idempotency problem. At the same time, I've solved the distributed problem. Guess what? That second request, it went to a different database. That's okay. I provided the ID. That database now knows about the same object. It knows the same identity as the other one. When they later talk to each other to try to sync up, hey, you know Bob 1945? Yeah, I sure do. Okay, same object. Cool, keep going. So this solves the idempotent and distributed problems at the same time. This particular one didn't suffer from the commutativity problem because this was the idea of creating a new object, and so we've provided the identity. So in this same application, perhaps there's still a commutativity problem because now I can edit Bob 1945. And so I'm going to put with a different body. And so those two won't commute. So we still have some work to do, but at least we've solved the ACID 2.0 properties for creating an object, creating an identity within the application. As a nice little benefit, we can also immediately free the user up so that they're not waiting on this operation to happen. Why is that? They already know the identity of the object that they're trying to create. So if the very next thing they want to do is edit that object, they can go ahead and edit the object knowing exactly what they're going to put their edit to, and they can stick that in a queue within the mobile application. And the mobile app itself can just run this process in the background. It can be the one waiting on the server and let the user go about their business. It can use the same identities for its own local database. You can have local storage on the phone using these same identities, and they're not going to be different from the identities generated on the server because you're not using auto-incrementing IDs in either place. You're coming up with the identity before you even get started. So that handily solves those particular problems. So that's how we can use ACID 2.0 to create better APIs. Next, we're going to talk about creating better messages. So again, I'll pause. Okay. So sounds like everyone's tracking with me. Cool. Now let's talk about messages. So we're going to build a microservices architecture with all sorts of queues and topics and mapping sagas and sending messages all over the place. So this is going to be fun. We've got an online store. So the person, the big boss who wants to buy that cool gadget goes to this online store, puts it in his shopping cart, submits the order. That puts a message on a topic saying, oh, the order has been placed. Maybe we're using Kafka to do that. Here it is. It's on the topic. The inventory system is subscribing to that, and it says, okay, the order's been placed. I'm going to go ahead and start kicking off my order handling process for inventory. Meanwhile, we've got another subscriber for the same topic. The accounting system is going to see the order has been placed, and so it's going to pick that off and start doing its accounting stuff, whatever that happens to be. So, meanwhile, back at the inventory system, it has figured out whether I've got these items in stock, and it's reserved those items, and so then it sends a items reserved event down a queue bound for the logistics system. It says, okay, items have been reserved. Okay, great. Now logistics starts doing its logistics things. Meanwhile, accounting has figured out, all right, we've got this order has been placed. We're going to go into our accounts receivable. We're going to create an invoice, and now there's our invoice event that gets pushed to a queue, and that gets sent off to the business portal. And now some poor guy on the other end who has to pay the boss's bills logs onto the business portal and says, oh, goodness, he bought one of these things. Okay, fine. He writes the check, sends in the payment, not the business portal, sends a payment down the response queue back to accounting to say, okay, this thing has been paid. Meanwhile, in logistics, we have picked, packed, and shipped the boss's big, expensive gadget, and now the logistics system sends a shipment message to the business portal. So you've got all these messages flowing through the system in order to fulfill this order. Lots of different parties involved, lots of different microservices. Just everything decoupled, everything beautiful, everything great. So how do we take a look at these messages and these message handlers and determine whether they are ACID 2.0? That seems like a tall order, but nevertheless, we're here. Let's do this. Idempotent. Let's just take a look at the order placed message. Is order placed idempotent? Well, let's see. Take one apart. All right, we've got the order ID, 123XYZ, and I've got some line items in there. Okay, so if this message handler is going to be idempotent, that means if I receive a second one for that same order, then all I have to do is ignore it. I've already handled that message. Just drop that one on the floor. Say, thank you very much. You don't even have to call that an error. You just say, oh, there it is. Already done. So as long as I do that, I'm being idempotent. So now I've just got a list of all the order IDs that I have processed. Everything's fine. Until you get this order placed message, same order ID, but different line items. What happened here? Well, somebody who wrote that web portal, or that shopping service, it allowed the user to hit submit. Things spun. Oh, wait a minute. Let me go back. Hit the back button. Add some more stuff to my cart. Submit the cart. All right, go forward. Submit again. And so it ended up with two different lists of items in that same order ID. So that system wasn't really protecting itself against pushing the submit button twice. Yep, that happens. How many times have you gone to a website that says, do not click submit twice? You'll be charged twice, or you'll get double shipment, or bad things will happen. That's just, they didn't know how to solve that problem. They didn't know how to make their web application idempotent. And so they just hoisted that upon the user, saying, nope, don't do that. Well, the user's going to do it anyway. So now downstream comes these messages that are modified in some way from the original one. What's the correct thing to do here? Well, if we're being idempotent and we have this list of order IDs and we see, yep, I already processed that order ID. Oh, okay, just drop it on the floor. Then I'm missing some of these items and my customer is not very happy. But if this was the first one that I saw and I see one of the others later, now I've got all of these items and the other one gets dropped on the floor. So I'm not being commutative. So what am I supposed to do here? Well, in order to implement idempotent messages, what I have to do is disallow this kind of shenanigans. I have to disallow a change to a message. So that means I'm not just talking about idempotent messages, I'm talking about immutable messages. I changed the title on you, I was sneaky there. So I want to make sure that my messages cannot change. So we talk about immutable objects in code all the time. So we've got language features that prevent us from changing values. That's great. Some data storage systems have immutability built into them. You can't update an object. You can't delete an object. You can only insert brand new ones. But when you're talking about messages here, these are ephemeral. They're flowing through systems. You have to make sure that this message cannot change. how are you going to do that? Because another copy of the message is coming along later. How can you guarantee that that copy of the message is exactly the same as the one that you just saw? Well, one way that I like to do that is that I use a nice little trick of hashing and a canonical form. Let me show you what I mean. Here is my invoice message. So I'm going to pretty it up a little bit, use JQ so that I can parse it and see what that JSON looks like. So we've got our invoice ID. The order is this order object with all these line items. Okay. So now what I want to do is I'm going to take out all the white space. So now I've just got this flat JSON object. What I'll also do is I will rearrange the properties so that they're in alphabetical order, and even do things like when I've got a list of things, I'll make sure that the list is also sorted in some way. So now I've got this canonical form that any invoice that looks like this is going to end up with that particular string. Which means that now I can take this, run it through a DGST, compute the SHA-512 of that object. That gives me this this big long hexadecimal number. If I take that as binary and then give me the base 64 of that number, now I've got this big old long string here. That string is the message ID. So that means that if I ever see that message ID again, I know it's exactly the same message. Nothing has changed. If I change the message, I'm going to get a different SHA. So within astronomical probabilities, we can talk about just how rare a collision is with SHA-250 or 512 here. Even with SHA-256, it's extremely rare. But 512, yeah, end of the universe kind of stuff. So so if you use this as the ID for deduping rather than some contents of the message like the order ID, then you don't have to worry about the message changing. You have immutable messages. It's built into your message identity. There's a nice little side effect of using hashes for identity is that you're always going to get the same hash no matter what machine you go to. So this is another great solution to the distributed property that we talked about before, where we had client-generated IDs. Well, if we use hashes, then anybody can generate the ID. They'll get the same number. It's really cool. So that's how I like to identify my messages, by the ID, the hash of their contents, not by any of the properties of the message, because the other things could possibly change if somebody made a mistake somewhere. So by doing that and making sure that your messages are immutable, now you are guaranteeing idempotent messages. Cool. So let's take a look at the other properties. What about commutivity? Let's think about this one. Yeah, okay, so let's suppose that the order is placed before the items are received. That sounds about right, or reserved. What if I reserve the items before I place the order? Well, that shouldn't happen, but the system should respond successfully to that. So I can probably design an algorithm that would make that work. Okay, let's suppose I've got that. And now let's say the item's reserved. What if that happens after the invoice or before? Well, that shouldn't matter. You can invoice in either order. That's fine. And now let's take the invoice compared to the order placed and evaluate those in either order. The items reserved and the payment, let's go ahead and swap those around. The shipment with the invoice. And we have to do this combinatorial just explosion of comparing message to message to see if they can happen out of order. And that gets rather tedious. Unless we look at the messages like this. This is a relationship between the messages where the arrows are pointing to the thing that should happen first. So the order is placed, and then you can reserve the items. Order is placed, and then you can invoice. So they're pointing back to their predecessors, the things that happened before. What about reserving items and invoicing? There's no arrow between them. There's no path to get from one to the other, following just the direction of the arrows. So that means they can happen in either order. So I don't have to worry about those things that are on separate branches. I only have to worry about the things that have arrows between them. So now, rather than this combinatorial explosion, I just look at 4 different relationships because I have 4 different arrows. Much easier to reason about. So what I've done here is I've put these messages in a partial order. Where I've got an arrow between them, then order matters. The thing that happened at the head of the arrow has to be before the thing at the tail. When there's no arrow, no path, then they can happen in either order. So the order is partial. It's not total. Partial order is another one of these mathematical concepts. So if you think about the numbers under the less than operator, you can take any 2 numbers, you can compare them, say, yep, this one's less than that one. You'll never get an I don't know. So the message is, or the order is total. So that means that you can take these, the counting numbers, you can put them in sequence. If things happen in sequence, they're totally ordered. But take a different operation. Suppose you're talking about contains, as in a word contains another word. So catalog contains the word cat. It also contains the word log. So that means that I could say one word contains another word, and if that's my less than operator, that's the way that I put things in order, then I can say, yeah, cat is less than catalog, log is less than catalog, but cat, log, how do they compare? Neither one contains the other. Yeah, either order is fine. So that's a partially ordered set, and a partially ordered operation. So what I'm doing here is I'm putting messages in a partial order. Now these arrows, as it happens, they don't just point to the things that happened before, my predecessors. They point to the things that I probably already need to know about. So if I'm going to reserve some items, I probably need to know about the order that was placed. If I'm going to ship something, I probably need to know which items were reserved. So it's really not a big burden to go ahead and carry that predecessor along with the successor, the thing that came later. So that means that what you can do is simply embed your predecessors within your messages. So this invoice that we just looked at, we've got this invoice ID. The order is an order message. It's not just the order ID. It's not just saying, hey, you pay me $3.45. I want you to be an invoice for order 123XYZ and leave it at that. That would mean that the system would have to look up in its own local storage, well, what was order 123XYZ? Okay, it was the order with these 2 line items, or worse yet, go talk to a different microservice and say, hey, you give me back that order. It's embedded. It's carried along with the message. So this solves the problem of commutativity of messages when you've got that arrow between them, when one of them is a predecessor of the other. Because if you received this invoice first, and then you received the order, well, you've already got the order within the invoice. You take this message, you look inside of it. Do you have any embedded messages within you? Okay, let me go ahead and process those first. As you process them, you're going to compute their hash. You're going to look up, have I already processed them in the past? You're going to be idempotent. So that means if you have, great. If you haven't, now's your chance. You have the message, you go ahead and do it. And then you pop the stack, you're back at the invoice, you process the invoice. We've gotten around the problem of commutativity by delivering the messages in order anyway. You have the predecessors right here. So to simply embed the predecessors, keep track of that partial order, and then where you don't have an arrow, meaning you don't have an embedded predecessor, order doesn't matter. Those could happen in either order. So this handily solves the problem of commutativity. Then we could also take a brief look at the, so we've looked at the idempotent commutative properties. We can take a look at the associative property, and we can see that what we're really doing here is we are collecting up a set of these messages. And as long as we've got this history of these are the messages I've handled in the past, I can compute their hash. I can see that I've already got this one. We're just doing a set union on the messages. So we're being associative. We can take a look at the distributed property. Everybody's going to compute the same hash. Everyone has the same identity for the message. We're distributed. So this handily solves the ACID 2.0 properties. Now, it does create some challenges. Before I get into the challenges, again, I'll pause. Hearing no questions, moving forward. One of the challenges is, okay, you've got these immutable objects, these immutable messages. Well, what if somebody wants to mutate? What if somebody has placed an order and they want to change their order? You just disallowed sending that that same order ID with some different objects in it. This is how you would update in this kind of a system. So you've placed an order. Now the user changes their mind, changes their cart, hits submit a second time with the express purpose of submitting a different order, not just trying to resubmit the same order, because resubmitting the same order gives you the same message ID. Everything is idempotent. But if they intend to change things, then what you do is you create a new message that embeds the predecessor, the thing that that happened before, the thing that it's replacing. So it says, okay, this order replaces that order inside of it. And now when you receive it, you can be commutative in that you know, okay, I've got this one that's on the inside, I've got that one that's on the outside. And then furthermore, you can know the relationship between the two. You can know that if I've already reserved these items, and now I'm taking a look at that order. Oh, okay, I see some new items in here. Let me just go ahead and reserve those two. Or I see these items have been removed from the order. Let me go ahead and cancel the reservations on those. So you can, knowing this relationship between the two, do the right thing with the difference with that knowledge. So updating a message is simply just sending another message where the previous one is a predecessor. Other challenge? Immutable objects. You can't change them. What else can't you do? You can't delete them. What if you need to cancel an order? That's an order canceled event. And its predecessor is the order that you're canceling. So that means that this flows through the system. It doesn't matter if the user was just really fast and like, oh, submit the order. Oh, nope, I didn't mean to do that. Hit cancel. And both of those messages left at the same time. Or if one of them got away and then the cancel chases after it. In other systems, you might say, oh, wait a minute, if it hasn't made it past this block, let me go ahead and delete those messages. Well, that's kind of playing with concurrency. It's gonna get kind of messy. So just let them go, let them flow through, and then when you receive this order canceled event, you can see inside of it, here's the order that was placed. Do I have that order? Have I already processed it? If so, go ahead and reverse it, cancel it out. If I haven't processed it yet, great. We can just go ahead and pretend nothing happened, just walk away whistling. So if you're going to replace mutation and deletion with immutable objects, then this is how you would do that. You just have your predecessors be the things that happened before. So taking those things into account, now we have defined a system of creating messages that are ACID 2.0. They are associative, commutative, idempotent, and distributed. And we've talked about strategies for making APIs that are associative, commutative, idempotent, and distributed. As long as you generate the ID on the client side rather than waiting on the server to do it, then you can have these 4 properties. As long as you have immutable objects that represent mutation rather than changing something under the hood, you can have these 4 properties. And these are properties that your application promises. They're not promises that you get from your database. But that means that now you can use databases that don't give you these promises. You don't have to rely on distributed transactions. You can work reliably and predictably in a distributed system, as long as you get the same results, no matter how you group things, no matter how you order things, no matter how you duplicate things, and no matter where you do things. This is ACID 2.0. And if you would like to learn a bit more about it, I have written a book called The Art of Immutable Architecture. You can go to immutablearchitecture.com and sign up for my newsletter. The book is just about to be available for pre-order. I will be the first to let you know when that happens. And in the meantime, you can get a monthly, or I'm sorry, not monthly, a weekly newsletter of all sorts of strategies you can use in order to build more reliable and robust distributed systems. And I thank you very much.
Nice. I actually have a question.
Mm-hmm.
I'm still trying to work through the like embedded messages.
Mm-hmm.
And so, like, let's say with your order example, you have the initial order, and then your update to the order.
Oh, okay. This one here.
Yeah, and that would contain a. So the second one would contain the first one.
Mm-hmm.
That was the. So the first one would hash to one ID. The second one would hash to another one.
Mm-hmm.
Then what if they played out of order?
Yeah.
So how would you have to store kind of like the hash for the first one, or?
Yes. Yeah.
For the embedded.
Yeah. So you would you would have the hash of all of the orders that you have processed, all the messages that you have processed. So yeah, when you see this structure come through, you would say, okay, let me drill in first, compute the hash of the order 1, 2, 3 XYZ, or pretend that this was an outer order containing an inner order. So this is an order replacement kind of a message. And then at that point you would see, have I already processed this message, and you would see whether you have that order in your history. A pattern that I hadn't really talked about yet that works really well with this is any sort of pattern that uses history as the source of your current state, like event sourcing. So you've got, rather than the current state of that order, you have all of those orders that played out in history. And so just going back through that history, you can see, okay, that was the one that I'm replacing, and you can just compute the delta from there. This I actually like to kind of tie this back to Git, because a Git commit is a snapshot of some files. It represents the changes you made to that to those files, but for for simplicity and speed, it was actually just a snapshot of those files. And it's got the hash of the previous commit, so it knows which one it follows. And so then Git can take a look at those two those 2 points in history and do a diff, and then compute rebases and merges and all that fun stuff. So this is basically you building that kind of intelligence into your application. So you can see, well, I already processed that order. There it is there. I know the current, the state of it then. Here's what I want it to be now. What's the different, add these items, delete those items.
Okay. Yeah, that makes sense. Cool. This is a, so does it get like, I guess, any more, because I know like when you're dealing with high throughput using like the DTC, it can really slow things down. Have you how have you found the performance with this approach, I guess?
Yeah, so I would say that there are faster ways to go. So if you are really careful and code things manually, you can find optimizations that this mechanism just avoids, because those optimizations are not provably correct. You have to think about each individual one. But the flip side is that you never have to be temporally coupled to a different service. So you never have to pause waiting for something else to complete before you can say, okay, that's done, and I can call that good. So so in your cap theorem triangle, this is completely AP. So this is always available because you're doing all of your operations locally on this machine. You've got the history that you need. I mean, tying it back to Git. If you take your laptop on a plane, you can still code, you can still make commits, because you have the local history of all of these individual commits. So as long as you keep a history of all of the events, and you can replay them in whatever order they happen to show up, then you can be autonomous. You can be isolated from the world. So so anything that you lose in terms of performance by not being able to do your own independent optimizations, you gain from the scalability of, you don't care how many other replicas there are. You're just concentrating on your own replica. And honestly, my favorite part of it is that you can be confident in the result. You don't have to think through all the different permutations. The math is already done.
Nice. Okay.
Renan, I know it's pretty late for you. Have we put you to sleep?
I'm still awake.
Cool.
So, are there any other questions?
No, not for me.
Comments?
Yeah, not for me as well. So, because I had the same thoughts about the size of the messages and the associated cost of transferring the data through the wire. But as it's like as of these many different iron triangles that you basically, if you want to achieve like two of them, you have to pay the price for the third in the third angle. So yeah,
that is true. And for a while, that was the biggest complaint that I heard from people about doing immutable architectures like this, where you've got things that don't change and you just store history forever. It's like, goodness, won't that grow unbounded? And that's becoming less and less of a concern that I'm hearing. But still, the truth is that the value of that history is immeasurable. I mean, Amazon gets extreme value from the history of people of orders that people have placed and didn't place. So you put something in your cart and then you abandon it, Amazon's still going to give you ads for it, and they're going to sell ads to a different site. You go somewhere else you didn't even know was associated. Hey, there's an ad for a thing that I put in my Amazon cart. So people are deriving value from this history, and so yeah, even though it does cost some money to save it, yeah, truth is the cost of storage is coming down. The value of history is only going up.
Cool. I'm gonna have to spend some time thinking about this, like how to, yeah. It's
Cool.
interesting. Yeah, I enjoyed it.
Awesome. Yeah, and that's why I wrote the book. Is that there's this leads you down into, well, now how do I solve this problem kind of things. So
Right.
like for example, this solution of replacing one value with another in order to simulate mutability. We didn't get into it in this talk, but if you've got two different people who could change a thing, and they could do so concurrently, now how do you resolve conflicts? How do you detect conflicts in the first place? And so there are solutions to all of those problems as well. And so basically, I traced all those boundaries, those trails to the boundaries, and then said, okay, this now is a complete system. And I've been using that system for my own architectures for a while, and so it's like, okay, I need to be able to give people the whole picture, because just having a part of it just starts them on a journey, but they need some help along the way. So that's what the book is really all about.
Cool.
Yeah, I would call the approach that you're describing as is what the functional programming is doing as a best practice. So that's the approach with immutable messages and distributed systems is equivalent of doing this in just a different setting. So quite nice.
Yeah, thank you. Yeah, it's really fun to apply this in a functional language. But most of the systems that I work on are in C# or in JavaScript. So I'm working right alongside the day-to-day developer, and they don't like to use Haskell and they don't like to use F#. So yeah, you do what you can, but it still works. The math is still good. You just happen to write your C# using immutable objects, and now with C#9, they're more baked in than they were before. That's awesome.
Yeah, and another thing we're thinking that if you have an existing system that you need to, that for example you're as an architect, as a developer looking at, and you want to understand, you want to identify what the flaws are, potential flaws, especially that impact scalability, resiliency. This is really fairly, I wouldn't call it simple, because simple means that you can take and use it. I won't be able to do it right now, but I really want to kind of put it the approach that you described into my toolbox as a way to basically do the audits of the systems that either I'm working on or my colleagues are working on, and provide some feedback.
Awesome. Yeah. And yeah. So I'd call back the reactive manifesto and reactive design patterns. Let me see if I can get that. Yeah, this book right here. That is where I first learned about these concepts. Well, there's a picture of the cover, but this is probably the best place to start when you're evaluating existing architectures, existing runtimes, and seeing how you can make incremental improvements to them. So my book will have some of that, but it's really about a complete system. This one lets you kind of walk there. Yeah. The other thing is the reactive manifesto, because everything's got to have a manifesto. If somebody hasn't already written the Immutable Manifesto, I bet they have. Then, but yeah, these are the different benefits you get from reactive programming, and whereas reactive programming is different from what I just talked about, it still kind of brings in this this ACID 2.0 idea. It does it through a concept very related to what we just talked about here, conflict-free replicated data types, CRDTs. So if you have an operation that's a semilattice, commutative, associative, idempotent, then that operation can be encapsulated within a data type. That's a conflict-free replicated data type. And then you have reactive programming where you subscribe to streams, and then you kind of pull your next result as a function of the previous result from a stream, that kind of build those up. Then you just run CRDTs through those streams, and you get these benefits. So cool stuff all around.
It's all really interesting. Cool. Well, thanks for taking some time to talk with us, Michael.
Yeah, thank you very much. I appreciate the invitation, and yeah, thanks to everybody for spending some time with me and having this awesome conversation. I really appreciate it.
Yeah. Cool. Well, I guess thanks for Not and Tommy for coming by, and
All right.
I guess we'll be putting up the next meetup sometime in the near future.
All right.
There you go.
Thank you very much.
All right.
Thanks. See ya.
Bye.
Bye.
Bye.